of those are bonus questions. They're at the very end. We'll use 2 Scantrons. I'll have those stuffed in your exam. But do try to bring number 2 pencils, so it's maybe more than one number 2 pencil. And maybe you've been seeing, I've been trying to give some updates on Canvas, so I would check the Canvas announcement section. Also, you guys, on the modules, in the old sample exam questions and keys, I tried to put a really rough breakdown of the number of questions that went with each topic. And some people said that kind of helps guide them how to, the best strategy for studying. So that hopefully will help. Yeah.
So are the bonus questions going to be a mix of things or is it like?
Yeah, they'll be a mix of things. So, because I know it is a long exam, I just made the last 18 questions, 18, I think. Bonus, just thinking if people run out of time, then they wouldn't panic as much, because those are bonus questions, right? The same strategy, folks, as with all the lecture exams. Just try to get through it once quickly. So if you hit a long, complicated question, maybe circle and come back to it later. If you hit a question that's like, oh, I'm not really sure, either circle it and move on, or circle it and guess and move on. Because it might be that towards the end of the exam, some of the questions, oh, you know those, inside and out. So just getting through the exam once will be really important. Also, you guys, make sure that you're actually getting your questions transferred to the Scantron form, right? When you take your board exams, your TEAS exam, all those things, right? You have to get the answer on the right part of the answer sheet or exam, right, for your credit. Okay, and then, so, you guys, any questions with regard to the final exam? I try to get the final grade submitted, ideally 10 days, even better 7 days after the final exam. So you guys don't use the Canvas grades. The Canvas gives you a grade, so don't use that grade. The grades will follow the point distribution in the syllabus. And if you think there was a mistake, you guys email me. I'm going to be out of the country and not checking email, so if you don't hear back from me, it's not because I'm ignoring you. I'll be back mid-January, and I'll just start going through emails. So as soon as I can, if I see that you emailed me and said there was a mistake, what we do is we plan to have a meeting here in the department, and we'll go over, all your graded stuff and try to figure out what the mistake was, and then we'll make the correction. So please don't panic if you don't hear back from me immediately. Any of you that need letters, like during that time, I can't write you a letter, right? So I just want to give you that heads up. Sometimes people write and they say, I need a letter by the end of the week, and during that time that I'm gone, I won't be able to help you out with it, if that happens to you. Okay. Any questions, general questions, you guys? Okay, so what we're going to do today is we're planning to finish the part 1 of our host defenses. We'll finish the non-specific innate immunity, and then we'll start the second PowerPoint, you guys, which is going to be a very superficial view of adaptive specific acquired immunity. Okay, but at least it'll give you, those of you that have never had any immunology, give you a little bit of idea of some of the key points. Okay. All right, guys, so last time we were talking about, started out with discussion of non-specific innate defenses. We started out with inflammation. We said there are many advantages to inflammation: increased blood flow, creating chemical concentration gradients, so will help guide our leukocytes to the scene of invasion. We talked about activation of our leukocytes. And we said one of the advantages of inflammation is it gets our first responders quickly to the scene of invasion. And so our first responders, you guys, are neutrophils. They're what we call professional phagocytes. And another professional phagocyte that we want to know about are called macrophages. They're slower to arrive at the scene, but they're longer lived, and they actually play an important role in not only killing microbes, but in activating adaptive immune responses. I'm just laughing, you guys, because that construction hum going on, I feel like we're like a flying saucer about to lift off. But anyway, so that's more of that construction noise in the background. At least they're not pounding on the back of the wall. Okay, so folks, last time we had ended with a quick discussion of phagocytosis. we said that the phagocytes will arrive at the scene of invasion using chemotaxis, concentration gradients of inflammatory mediators and microbial products will guide them to the scene of invasion. And we're hoping that our phagocytes will have cell surface receptors that can bind to some part of the outside of the invading microbe, because the phagocytes first have to attach before they can perform the process called phagocytosis. So just really quickly, guys, we said in this process, the microbe is brought into the interior of the phagocyte in a membrane-bound vesicle called the phagosome. It's literally called an empty body. And we said that for the microbe to be killed, there were two strategies that phagocytes use. One is called oxygen-independent killing. This is killing by the hydrolytic enzymes delivered by the lysosomes. Right? The lysosomes fuse with the phagosome, forms a phagolysosome. We said those digestive enzymes, those hydrolytic enzymes, are what we call acid activated. They're only going to fold into the correct functional conformation at low pH. And that's going to be achieved, you guys, by proton pumps and the phagolysosome pumping protons into the interior of the phagolysosome from the cytoplasm. So we have acidification of the phagolysosome, and that's what will activate those digestive hydrolytic enzymes. So that's called oxygen-independent killing, because we don't see an increased use in molecular oxygen for that first blow, right? The second blow, the 1-2 punch, is called oxygen-dependent killing. This process sometimes is referred to as the oxidative burst or respiratory burst, because we see a huge consumption of molecular oxygen. And the reason is that enzymes within the phagolysosome are making those really toxic reactive oxygen intermediates, such as superoxide, anions, hydrogen peroxide, even bleach-like substances, right? So they're using a lot of molecular oxygen. So that's like the second blow, or the second punch. So hopefully with those two mechanisms, you guys, the microbe will be destroyed, nutrients can be absorbed, then waste will be present here, we call it waste vesicle, and the waste then will be dumped to the outside of the phagocyte via exocytosis, and the opposite of phagocytosis. Now, we want to recognize, you guys, that sometimes in chronic inflammation, say when the host immune response can't kill the microbe, and you have chronic inflammation, chronic meaning over a long period of time, attracting phagocytes to the scene of invasion, there's a couple of problems there, because phagocytes have a lifespan. The neutrophils, we know, only live a few days. The phagocytes can live longer, but eventually they die. So when our phagocytes die in lice, they're going to release all those toxic hydrolytic enzymes, release all those toxic reactive oxygen intermediates into the outside of their cells, and thus, you guys, those phagocytes, when they die, they're actually going to cause harm to our cells, our tissues, right? And furthermore, I think we mentioned this, you guys, sometimes when phagocytes are feeding, the lysosomes, who knows why, the lysosomes, instead of fusing with the phagosome, the lysosomes will migrate and fuse with the cytoplasmic membrane, dumping those hydrolytic enzymes into the extracellular environment. And there they too can cause damage to our cells and our tissues. So you guys, this is another example of that double-edged sword of the immune system. Remember, the double-edged sword, we have one cutting edge here that protects us from invading microbes, but the opposite edge is also cutting edge, and that opposite edge can actually hurt us. So we always want to remember this delicate balance in the immune system. We can't live without it, but in many infectious diseases, it's actually the immune response that's causing most of the damage, right? Yeah.
So if somebody has chronic inflammation, then what's the outcome like that? It just keeps swelling and swelling and swelling?
Oh, yeah, that's a really good question.
There's no way to get rid of it, or?
Well, that's sometimes, like, of course, the first goal would be to try to get rid of, if it's a microbial infection, you can't get it, you try to kill the microbe if possible. The problem is sometimes with the phagocytes dumping a lot of these damaging enzymes and reactive oxygen intermediates, you get so much host cell tissue damage, you end up with fibrosis. And fibrosis is when functional cells, functional tissues, become non-functional. So that's a problem, is that you start losing functional cells, depending on where the inflammation is occurring, right? So you know, potentially then you start getting a decrease in the function of the normal host tissues. So sometimes, and I know in vet medicine, they told us watch out, because a lot of times what people want to do is to use steroids, because steroids are anti-inflammatory, but long-term steroid use will have problems, right? And so we were told, don't use steroids just to cover the symptoms. You know, you want to try to find out what is wrong and try to address what's actually wrong. Is it a chronic infection? You know, get in there for the microbe. Because steroids are easy to use, but long term they cause problems too. Yeah. So in chronic inflammatory disease, they probably will use some kind of immunosuppressant therapy, trying to calm down the immune response. But again, you gotta remember, then your patient's gonna be compromised. So then you have to be really careful about them thinking of options. So it's a tough one. It's a tough situation to deal with chronic inflammation, yeah. So folks, just really briefly, way back in medical micro, we talked about facultative intracellular parasites or pathogens. We were using specifically bacteria who have evolved ways to live within, like macrophages, right? And so some of the strategies they use, you guys, is some of the microbes have learned how to block the proton pumps. So you won't get proton pumping into the phagolysosome, you don't get the drop in pH. So those lysosomal digestive enzymes, hydrolytic enzymes, they never are activated, right? So that's one way the microbes can prevent that first blow, right? And then other microbes, it's really interesting, you guys, they have a way of preventing fusion of the lysosome with the phagosome. So you never get the hydrolytic enzymes dumped in there, and you'll not, in addition, you won't get the reactive oxygen intermediates made. And another sneaky way, you guys, to live in a phagocyte is if you can escape from the phagosome, like penetrate the membrane of the phagosome and just live here in the cytoplasm, and the phagocytes can't harm you at all. So again, you guys, we've seen it's this coevolution between us and the microbes, right? So through natural selection, we're selected for abilities maybe to kill the microbes. And then through natural selection, there's selection of microbes that figure out a way how to outwit, right, our immune response. So always going on, kind of like an evolutionary cha-cha-cha. All right. So let's just make a list up for you guys. So in talking about innate defenses, you'll recall we first talked about inflammation. Changes in increased blood delivery make our vessels leaky, so our leukocytes can leave the blood vessels and move to the area of invasion, get activation of our leukocytes. The leaky vessels permit other antimicrobial compounds, which we'll be discussing, to leave the blood and diffuse to the area of invasion. We get delivery of our phagocytes, so we get phagocytosis there, so all those advantages of inflammation. And then we've talked about specifically, you guys, about phagocytosis, how hopefully if we can get our neutrophils quickly to the scene of invasion, they can quickly phagocytize and kill any invading microbes, right? And then, you know, we just block infection right off the bat. Another non-specific defense, you guys, is fever. And you might recall that we described substances that trigger, fever production are called pyrogens, pyro for fire, right? And folks, in the old days, we would describe two types of pyrogens. Exogenous pyrogens, meaning pyrogens that come from outside of our body, they aren't pyrogens we make. And the classic one is endotoxin, the lipopolysaccharide gram-negative bacteria. Because when we get massive release of endotoxin, right, it's going to trigger release from our white blood cells of what we call endogenous pyrogens, substances we make, right? And so for some of the endogenous pyrogens, and you don't have to memorize these, I won't ask you specifically on the final exam, but some example of endogenous pyrogen cells of our immune system release. Tumor necrosis factor, and I think it's tumor necrosis factor alpha, interleukin 1, and interleukin 6. So these endogenous pyrogens, they circulate in the blood to the brain, where they trigger our brain to reset our thermostat, resetting it to a higher temperature. And then it's just fascinating, you guys. So then our body goes through all these adaptations to try to increase our core body temperature. So for example, you guys, the blood vessels in your periphery might constrict, vasoconstriction, to reduce blood flow to the periphery, to reduce heat loss, right? So you're saving more heat. You literally, guys, you might start shaking. The muscle contractions are going to generate heat. And you'll undergo behavioral changes. You might feel cold. So you might put on maybe another jacket, or if you can, you might stay at home and crawl into bed and throw a couple of more additional blankets on your bed. You might turn up the thermostat in your home, right? Trying to increase the temperature. And we might say, you know, again, as evolutionary biologists, we're like, well, why is that? What advantage is that? Why was there natural selection for that? So it's really interesting, you guys. Some microbes are actually inhibited from replicating, or it slows down replication when we increase the temperature. So that might be one reason there was selection for our ability to generate a fever, is it might actually inhibit the replication of some microbial pathogens. And then, you guys, this makes a lot of sense to me. Remember in inflammation, remember in phagocytosis, there's a lot of chemicals that are being released. And if we take phagocytosis, you guys, we talked about the hydrolytic enzymes, we talked about the enzymes making those reactive oxygen intermediates. Those reactions will all be increased, they'll all be sped up at higher temperatures, right? So that means your phagocytes will be more effective killers, right? You might get more efficient chemotaxis, for example, right? You might get better production of inflammatory mediators. So it's thought that for these reasons that fever was selected for part of our natural defenses. Now, this is really interesting, you guys, because in general, I think if you ask people around the world, they think us Americans, we're kind of wusses, we don't want to be uncomfortable. And indeed, because we don't like how we feel when we have a fever, there's a huge market in over-the-counter antipyretics. What do you think an antipyretic is? Something that will reduce fever, right? Yeah, so the classic one used by indigenous people is aspirin. And then there's many subsequent antipyretics that you can buy, including ibuprofen, acetaminophen, and I think there's a whole slew of others. But some people would argue, if you're healthy, right, and if the fever isn't too high, too extreme, maybe you shouldn't take antipyretics, right? If it's part of your normal defenses, right? You know, and again, as long as it's not too high and you're healthy, otherwise maybe you want to let the fever go for a while, because it might actually be helping to inhibit replication of the pathogens, and it's increasing the killing efficiency of your immune system, right? And to me, you guys, it's so interesting. Like, folk medicine to me is just so cool. So there's many cultures who, for health, what do? They build a sweat lodge, or they build a sauna, right? Where they purposely go into this really hot environment. It's often thought is healing or healthy for you, you know, preventive. And it's like, you know, it kind of starts to make sense when you recognize the advantages of that increased temperature. We always need to be careful, though, you guys, of our high risk people, like, so little babies, little children. I was constantly on the phone with our healthcare provider when my kids were spiking fevers, wanting to make sure, are we still okay? Are we still okay? You know, is it still okay to let this fever go, right? And older folks, anybody immunocompromised, I would be in constant touch with my healthcare provider, you know, to make sure that we're still doing okay. It was interesting yesterday, the conversation that was generated, because one of your colleagues was saying for their young child, the doctor had said, oh, like a fever of 104, it's okay. And I was kind of like, wow, as a parent, I'd probably be freaking out, you know? And then it generated this conversation about like all the different advice people have gotten. And so other people have gotten the advice of like 102, you know, especially again in a high risk maybe a 8-year-old child, be in contact with your healthcare provider. And another of your colleagues said that when their child got to like 102, they would start having seizures. And of course, that means like, all right, we're going to the emergency room now, right? So I think the thing is, you guys, is to always touch base, with your healthcare provider, monitoring the fever. Ask them for their advice of if an antipyretic, is called for, which one would be the best one, right? Because sometimes kids have trouble. I think it's with acetaminophen, Tylenol, you guys. I think it's easy to get kids on this. I think it can cause some liver damage. So, and I know you guys are going to be the healthcare professionals in the future. So I'll be calling you maybe about my grandkids, right? And you can tell me what I should be doing. But yeah, again, you guys, the double-edged sort of immune system, right? Fever can be helpful, but too high, maybe too high is not good either. Okay, folks, so we did fever. The next one we're going to do is the complement system activation. And this one, you guys, could be a whole lecture all by itself. And so we're just going to hit the key points, you guys, on the complement system. So it's called a system because it consists of about 30 proteins. Most are made by the liver. And so this would be of concern in your patients if they have serious liver disease. You're going to recognize that part of their innate nonspecific immune defenses are going to be lower. Their complement system, they might not be making the right proteins. And these proteins, they circulate in body fluids in an inactive form. And to be activated, they have to be cut into 2 pieces. Okay? To activate, complement protein is cut into 2 pieces. And I'll just use an example here, you guys. This is a little cartoon of the terminal complement pathway. So the complement proteins, you guys, they either receive numbers or letters. So this terminal pathway, we can see this complement component C3. So this is just an example. And for to represent complement, we use a big C. Okay. So here's our big inactive C3 protein. And for it to be inactive, we have to cut it into 2 pieces. And usually the 2 halves, they're labeled little a and little b, almost like a Dr. Seuss story. So we have C3a and C3b. And it's these cut activated pieces then that will carry out their biological activity. And furthermore, you guys, it's so cool. Once one complement protein is activated, it activates the next protein in the system, and then that one activates the next protein. So it's like a domino effect. Or some people call it a cascade. Like once one complement protein is activated, the remaining proteins will be activated. And furthermore, you guys, what's really cool is that each activated complement protein can activate several other of the next proteins in the system. So we'll just use this example, you guys. I know this is hard to see. Here's our complement component C3 that's been activated, split into C3b and C3a. So one function of this C3b is it will activate complement component C5. It will activate complement component C5, causing this guy to be cut into C5a, and C5b. But furthermore, you guys, this one activated complement, it can activate maybe hundreds of the next one. So this one activated C3b, it can activate maybe 100 C5s. And this phenomenon, you guys, when one protein activates many additional proteins, it's called amplification. So activation of the complement system, you guys, is referred to as an amplifying cascade. Amplifying because you can start out with a tiny, tiny trigger, like the invasion of just a few microbes, right? Little tiny guys. But once they activate one of the complement proteins, they, as a consequence, are going to activate lots and lots of other complement. So you get this amplification, a large response based on a tiny initial trigger, right? So amplifying cascade, and it makes it really effective. Now, what we want to know, you guys, is so what's the benefit, right? We're always going like, well, so, you know, why is activation of complement helpful? So let's make a list of all the cool things that the activated complement proteins can do. So we'll make a list, you guys, of the functions of activated complement, and it's pretty amazing how diverse their functions are. And I'll just use a PowerPoint slide, you guys, so I'll just write down what's on the PowerPoint slide. So first of all, you guys, it's really cool. The activated complement proteins can help release more inflammatory mediators, right? So activated complement is going to help increase the inflammatory response. And remember, you guys, when inflammation is occurring locally, right, it's very beneficial. We're increasing blood delivery to the scene of invasion. We're increasing delivery of white blood cells. We're going to increase delivery of antimicrobial compounds. We're triggering the walls of the vessel so that leukocytes will stick and squeeze their way through it. We're generating all of those chemicals that create the concentration gradient that guides the phagocytic cells, white blood cells to the scene. So inflammation locally and for a short period is really good. So activated complement will help increase that local inflammatory response. And then, you guys, it's so cool because the activated complement, they help create that chemical concentration gradient that will guide our phagocytic cells, guide our white blood cells to the scene of invasion. And the chemicals, you guys, that make up that concentration gradient, we call them chemotactic factors. Okay, so activated complement, they're going to act as chemotactic factors, helping to set up that concentration gradient, guide our phagocytes, our leukocytes, white blood cells, to the scene of microbial invasion so they can carry out their work. So that's really cool. And then the third function, you guys, is this is so neat. The activated complement, they can act as what we call opsonins. So this is a new term, you guys. So opsonins are substances that will coat the surface of an invading microbe and literally make the invading microbe stickier for our phagocytes. So this process, you guys, of coating an invading microbe with it like a sticky substance is called opsonization. The process is called opsonization, and it literally means preparing to eat. Now, you guys know eating is like my favorite pastime. So I always have to have some kind of, food analogy for this. So guys, I think of opsonins as being delicious, rich, sticky chocolate sauce. So when the microbe invades, we're going to pour sticky chocolate sauce all over it. And then the phagocyte has receptors for the opsonins. So those opsonins, the sticky chocolate sauce, permits the phagocytes to bind more efficiently to the invading microbe. So that's going to increase phagocytic killing, right? So opsonization, preparing to eat. So we're gonna cover the pathogen with complement. And here, you guys, we say complement is the opsonin. And then the phagocytes have receptors for the complement. And then the result is we're going to increase phagocytic killing of the pathogen. Okay, Sonic chocolate sauce. Okay. And then you guys, the last really cool thing that activated complement can do, it's wild. The activated complement proteins can insert themselves into lipid bilayers, into cytoplasmic membranes, in the outer membranes of gram-negative bacteria, into the envelope of viruses. And they literally create a pore, a hole. And this little pore or hole that the complement forms, you guys, is called the membrane attack complex. So again, you guys, it could be cytoplasmic membrane, it could be the outer membrane of gram-negative bacteria, it could be the envelope of a virus. So it forms a membrane attack complex. So again, you guys, thinking of food, I always think of a Mac attack, like I always think of hamburgers, although I know that's not good for you. But anyway, it's not good for the invading pathogen. So in cellular organisms, you guys, if you get the membrane attack complex formed in the cytoplasmic membrane, that causes the cell to be leaky. And that's going to kill the cell, right? You might get lysis just with that. If you have membrane attack complex in the outer membrane of a gram-negative bacterium, that hole lets complement enter, cross the outer membrane, and then the complement can form a membrane attack complex in the cytoplasmic membrane of the gram-negative bacterium, will kill them that way. If we have a membrane attack complex formed under the envelope of a virus, could that interfere with the ability of the virus to attach to another cell? Yeah, remember guys, any kind of damage to envelope virus's envelope usually makes them no longer infectious, right? So Mac attack is really cool. And I think this next slide, you guys, yeah, this was just to show you electron micrograph of the cytoplasmic membrane of an erythrocyte, a red blood cell. And it looks to me, you guys, like somebody took a machine gun, you know, like, so what are all these holes, do you think? That's the Mac attack, right? And you see, oh my gosh, that red blood cell, you know, not long to the world with that many holes or pores in its membrane. So you can see how effective that membrane attack complex can be. And then, folks, the last non-specific innate defense we're going to talk about over here is called alpha and beta interferon. And what I'll do, you guys, we're at the end of our board here, so I'll erase this to do some more cartooning. But you guys, alpha and beta interferon, maybe think of interferon interferes with viral replication. Inhibits viral replication. And we'll cartoon this, you guys, because it's just an amazing system. I mean, your body's, your immune system is truly amazing. So are you guys all right if I erase this? Remember, most of this is on the PowerPoint slide. And also, you guys, in the supplemental notes, the supplemental lecture notes. Okay, so if we're talking about human interferons, there's actually three types. And we use the alpha, beta, gamma symbols. So alpha and beta interferon. And it's usually abbreviated, you guys, IFN, and then you put the symbol afterwards, so it'd be IFN alpha, IFN beta. These interferons are the ones that will inhibit or interfere with viral replication. So these are the two we're going to talk about right now. The third one, you guys, is called gamma interferon. Or IFN gamma. This one is actually plays a role in adaptive immunity, specifically in cell-mediated immunity. So this will be later then, when we talk about cell-mediated immunity. The second PowerPoint. Okay, so right now, you guys, we're just going to talk about alpha and beta interferons. Right? So. Let's pretend pretend, you guys, that maybe we just got infected. Let's say we just got infected with some virus. So let's say this is the circle with an N is a nucleus. Let's say this is the human cell. And there's some neighboring human cells over here. All right, and let's say this is early in viral infection. So let's say, you guys, this first cell has been infected and the viruses are replicating. Okay. Well, what this first infected cell can do, you guys, is just amazing. It can release a chemical alarm. It can release a chemical alarm to alert surrounding cells, we're being invaded. Get out your weapons. Be prepared to be invaded. And you guys, what do you think the chemical alarm is? What do you think the host cell makes? What are we talking about here? Yeah, the chemical alarm that the infected cell makes is the alpha and beta interferon. So that's the chemical alarm. So we'll call this the alarm, right? And what's so cool, you guys, is that the neighboring cells, they have receptors for that interferon alpha and beta. Okay, so which are they? I'll make them little red dots, you guys. We'll make these little red dots. So when the alpha and beta interferon bind to the neighboring cell, it sets off a cascade of events that triggers the neighboring cells. So the IFN alpha and beta trigger neighboring cells to make antiviral proteins. These are kind of like the weapons that the neighboring cells are going to use, antiviral proteins. And of course, you guys were notorious for abbreviations. Okay. So when the neighboring cell that hasn't yet been infected, when the alpha beta interferon binds to the neighboring cell, it sets off a series of events. So the neighboring cell starts making these antiviral proteins. And this is beautiful, you guys, because that means we'll make the antiviral proteins. You guys are running out of colors here. Let's make them blue. We'll make them blue. So by the infected cell alerting the neighboring cell early enough, the neighboring cell can start making all these antiviral proteins, the AVPs, so that when this poor little infected cell, when it's perhaps is killed, right, releasing all of the new invaders, all the new viruses, and they come over here, and the viruses invade, all these antiviral proteins are already present. And the antiviral proteins, they can block, they can destroy viral RNA, they can block translation, right? So the antiviral proteins will, the AVPs, block viral replication. So this cell will be okay, right? This cell is going to block that virus from being replicated, right? So there'll be no viral infection. So to me, you guys, all this stuff, it's like a Greek drama or a Shakespeare drama. It's like this little cell is a sacrificial lamb, right? It's probably going to die, but before it dies, it's going to alert its neighbors so that they can protect themselves. Yeah. And so what's so cool, you guys, if you can get early release of interferon alpha and beta, you can stop the viral infection. Just keep it in a really tiny localized area, because all the surrounding cells are ready to stop the viral replication if they get infected. So again, if the system is working quickly, it has to work quickly, right? You might not even know that you have that virus, right? You block the infection. pretty amazing stuff, isn't it?
Is there a way to like, recreate that? So like,
Oh, they have recombinant interferons? Yeah, so they
purposely.
yeah, they can make recombinant interferons. I'm most familiar with it in cancer therapy, which I think are using, oh my God, I'd have to look at this, you guys. I wanna say maybe gamma interferon in cancer therapy, but I need to look that up to verify it. But definitely they're using recombinant interferons for drug therapies. Yeah, absolutely. Yeah. Okay, you guys. So with that, then we've come to the close of our very brief, exploration of innate non-specific defenses. So you guys, and I don't mean to be sound funny, but do you have any questions on if you have a chance to think about some of those earlier topics? Okay, we're just let's just do this. I agree. Let's just do this, you guys. All right. So, folks, we're gonna finish then with the last PowerPoint. This is the last PowerPoint of your Bio 440 adventure, and this is the other branch of our immune system called adaptive specific acquired immune responses. Okay, so you guys, I'm gonna erase this. So we'll start out with a new board. Defenses or immunity. Remember we talked about non-specific innate, which we just finished. And you recall, you guys, this is always on, so it's really fast. So there's a real fast response. It provides broad protection against a wide range of microbes. But you guys, there is a disadvantage with our non-specific innate defenses, and one disadvantage is it doesn't exhibit what we call immunological memory. But no immunological memory, and we'll explain what we mean by immunological memory here, you guys. Okay, so we'll just leave it at that. So the hope is, folks, is that for most of the microbes that invade us every day, we're constantly being invaded by microbes. The hope is, as long as they're really, really low virulence microbes, probably non-specific innate defenses are going to take care of them. So probably every day you guys are being protected by our innate non-specific defenses. But you guys, the concern is, what if you encounter a highly virulent microbe, right? Remember all the virulence factors that Staph aureus has? Yeah, so these highly virulent microbes, they often have virulence factors that lets them outwit or avoid or destroy our non-specific defenses. So then we're like, oh my gosh, so do we have any backup troops, right? We're going down. Where's Gandalf, right? Okay, and so it turns out that we do, you guys. We have another set of warriors, we could say, and those are cells that are involved in what we call the adaptive. And it's had several names, you guys: adaptive, specific, acquired immunity. Okay. So acquired means it's not always on. We have to be exposed to the pathogen. We have to be exposed to the toxin. And then it takes a while for the response to develop, right? So a disadvantage, you guys, is that there's this lag period. It means it's not going to turn on instantly. It takes a while for it to develop. So that's a disadvantage. It's specific, you guys, it's usually going to be active only against the pathogen or the toxin that you were exposed to, right? So you might say that's kind of a disadvantage, right? Adaptive, this is so cool, you guys, because it lets you adapt to the pathogens in your environment. If you survive, the huge advantage is that adaptive immunity does exhibit what we call immunological memory. And what this means is every time, you guys, we're exposed to a pathogen, we make what are called memory cells. So memory cells are made. And these are going to be memory, right now this might not make sense, you guys, but this will eventually make sense. So we're going to make memory B lymphocytes. And memory T lymphocytes. So if we survive, you guys, that initial infection, our body then has all these memory lymphocytes that literally remember that pathogen or remember that exotoxin. So that if we are ever subsequently infected with the same pathogen or exposed to the same toxin, those memory cells activate instantly. So as a result, we have what's called a secondary immune response. And the secondary immune response is going to be, these guys trigger a secondary immune response. The second time you see the pathogen, the second time you see the endotoxin. And this secondary immune response, you guys, is going to be faster, stronger, longer lasting than the first immune response, which is called the primary immune response. And so, folks, it's these memory cells that are responsible for lifelong immunity against pathogens. In the old days, you guys, like if you were lucky and let's say smallpox moved through your town and maybe you got smallpox and you survived, subsequently you would never have to worry about dying from smallpox because you had memory cells, so that subsequently, it could be years later, if you ever got infected with smallpox virus again, those memory cells, boom, instant activation with a stronger, faster, longer lasting, more effective, more efficient secondary immune response. So that's the basis of lifelong immunity. You guys, it's also the basis of vaccination. Yeah. When we vaccinate, you guys, we're purposely triggering memory cells to be produced against a pathogen, against an exotoxin, so that if we ever do become infected with a highly virulent pathogen or exposed to that highly virulent exotoxin, those memory cells, boom, they're instantly activated. Strong, fast, highly effective immune response. And that's why we're protected, is by those memory cells. And you guys, did non-specific innate defenses have memory? Nope, no memory cells. It doesn't matter how many times you guys, like I get a staph aureus infection, my inflammatory response will be the same, right? So again, you guys, immunological memory is just awesome. It's amazing. Basis of lifelong immunity, and also the basis of vaccinations. This is why our vaccinations work. So vaccinations are based on generating those memory cells. So that's just the coolest thing. Okay. So, right. Okay, so again, you guys, just kind of recapping. So adaptive immunity is specific for a pathogen or a toxin. Which some people say, well, that's kind of a disadvantage, right? Because wouldn't it be great if it was it was so effective against all pathogens? And a big disadvantage, you guys, is that there's this lag period. It takes a while for it to be activated the first time we're exposed to a pathogen or a toxin. But you guys, this is a huge advantage of adaptive immune responses, is the immunological memory. The faster, stronger, longer immune response the second time the pathogen is encountered. Okay, guys, so adaptive specific acquired immunity, again, it has like two branches. Like, remember, it's kind of like the military. We have branches of the military. So in adaptive immunity, there's two basic branches, and then there's some sub-branches. So the two branches, you guys, we'll spend most of the time talking about humoral immunity. Humoral means fluid. And so it's like, well, what's important about the fluid? It's in the fluid portion of blood, the fluid portion of the fluids the fluid that bathes our cells, contain antibodies, also known as immunoglobulins. And you guys, our abbreviation for immunoglobulin is IG. So whenever you see capital IG, that's telling you that we're talking about an immunoglobulin, an antibody. And so these antibodies, immunoglobulins, you guys, they're best at providing protection against extracellular pathogens and toxins. So we're going to see, you guys, the way the antibodies protect it is by binding to the pathogen or binding to the toxin. Once the pathogen or toxin gets inside our cells, our antibodies cannot cross our cytoplasmic membranes. So that's why usually humoral immunity antibodies provide protection against extracellular pathogens and toxins, right? But we know, you guys, there's a lot of intracellular pathogens, like all viruses are obligate intracellular pathogens. So do we have any protection against them once they get into our cells? And the answer is yes. And that's the protection against those intracellular pathogens will be offered by cell-mediated immunity, CMI. It always seems to me that should be this awesome television series, Friday nights at 8, CMI, immune response. Okay, so cell-mediated immunity, and as the name tells us, you guys, this is protection provided by cells of the immune system. And the two groups of immune cells that we'll be discussing are what are called T lymphocytes and activated macrophages. So it's cool, you guys. The macrophages, we could say the macrophages are kind of bridge cells. They're involved in innate nonspecific defenses, but they're also involved in adaptive immunity. So they're kind of like a bridge cell between the two systems. And then, folks, with NCMI, we're going to use two different examples, you guys. We're going to show activation of what are called cytotoxic T lymphocytes, and we'll cartoon this, you guys. Cytotoxic T lymphocytes, and sometimes you use a big T, you guys, for a T lymphocyte, and then you use a subscript C for cytotoxic. These are T lymphocytes that are going to recognize our cells that are infected and destroy them. Yeah. And then the other example we use, you guys, will be activation of macrophages parasitized by those facultative intracellular pathogens. And the example we'll use, you guys, is Mycobacterium tuberculosis. Because remember we said that Mycobacterium can actually replicate inside our phagocytes, right? So we're going to figure out how does the immune system, activate the macrophage to kill the Mycobacterium. Don't let them replicate inside of you. Do your job. Right? So you guys, this is kind of the big overview. And so you guys, just to make sure that I hit all the points here. So humoral immunity provided by antibodies and immunoglobulins, primarily provides protection against extracellular pathogens and toxins. And what we're going to discover, you guys, is B lymphocytes that actually make our antibodies, right? And then the second branch, you guys, cell-mediated immunity. This is protection against intracellular pathogens, and we'll talk about activation of cytotoxic T lymphocytes and activation of macrophages. Just as an aside, you guys, and we won't talk about it, but in A&P will, CMI also provides protection against cancer cells, which we won't talk about. And it's also the branch, you guys, that's responsible for transplant rejection, right? So this is always an issue if you're transplanting tissues or organs. But we're not going to talk about it, you guys, but just to know there's other functions or issues related to CMI. Okay, we're just gonna talk about intracellular pathogens. Okay. And so folks, because, we only have one lecture more. And you guys, immunology is usually taught as its own course, a whole semester-long course in immunology. So again, you guys, we're just kind of getting the appetizers here. And I thought we have so little time to talk about adaptive immunity, I thought, well, what is kind of the concept that I'd like you guys to have? And my thought was, if you guys can understand how HIV cripples our adaptive immune response, then you have the big picture. So you guys, I'd actually like to take some time to do a concept map showing the key role of T helper lymphocytes and how they cripple all branches of adaptive immunity. So we can understand how it is that HIV causes death indirectly by crippling the immune system. So folks, you might want to start out with a new piece of paper, maybe a landscape version, because I'm going to do a pretty big concept map here. It's going to be a lot of repetition. It's just like another way of showing the branches of the immune system. But then we're going to talk about specifically, how does HIV cripple this? And the whole key is, you guys, is that HIV destroys the most important cell of the immune system, our CD4 positive T helper lymphocytes. So we're gonna explore the key role, you guys, and how the T helper lymphocyte helps coordinate the cells that are involved in humoral and cell-mediated immunity. Okay. So this might be like repetition, but for me, the more things are repeated, the better. It's like eventually on the 10th or 20th time, I'm like, man, I think I get it. Especially with immunology. Okay. So we can label this, you guys, the key role CD4, you guys, is a surface molecule that helps us identify different cells of the immune system. So these specific lymphocytes are called CD4 positive T helper lymphocytes. And their name tells us, you guys, they're going to help all the other cells of the immune system. So we're looking at key role of CD4 positive T helper lymphocytes, and we go TH, you guys, in adaptive immunity. Okay, so we want to put our CD4 positive hero right here. So this is like my handle of the immune system. So here's our conductor of the immune system. Like if all the cells of the immune systems, you guys, were like a band or a symphony or an orchestra, the T helpers are the conductors. They tell which cells, now it's your turn. Now you need to respond. And you cells over here, you need to quiet down. We don't need you right now. So the T helper offers guidance to all the cells of the adaptive immune response. So how will the T helper do this, you guys? The T helper doesn't have hands, right? The T helper can't talk, or can they? Could they talk using chemical messengers? Yes. Yeah, right. So you guys, that's how the T helpers are going to guide all the other cells. They're going to provide chemical messengers. And you guys, we're just trying to simplify this. So these chemical messengers that the T helpers make to guide all the other cells, we're just going to call them T helper cytokines. And there's many different types, you guys, and we won't go into them. We're just going to call them T helper cytokines. And we'll use this little symbol, you guys, like a kind of a jagged arrow, to indicate the release of T helper cytokines and their target cell. Okay. So again, you guys, long landscape-wise, we'll divide our concept map here. This side will be humoral immunity. On this side, and then over here will be cell-mediated immunity. And what we'll do, you guys, is we'll first fill in the target cells. The cells that the T helpers are going to help. So over here in humoral immunity, guys, the T helpers are going to guide B lymphocytes. Sometimes they're called B cells. And the function, you guys, of B lymphocytes is to make antibodies. That's their function. They're gonna make the antibodies, the immunoglobulins. So that's the site. The two cells that T helpers are gonna help in cell-mediated immunity, guys, are gonna be our cytotoxic T lymphocyte. And these are often called CD8 positive because they have a different molecule, cytotoxic T lymphocytes. And then the other cell in cell-mediated immunity that the T helpers are gonna help are gonna be macrophages. So these are gonna be our, and we're gonna say a resting macrophage. Okay. So folks, let's first tackle how T helpers will help coordinate responses for humoral immunity. So our target cell, you guys, will be what? Who's gonna make our antibodies? Yeah, the B lymphocytes. Okay. So we're gonna do just a really quick overview, you guys, of what's going on with our B lymphocytes. Okay. So if we look at activation of B lymphocytes. So we'll see that the B lymphocyte is going to bind to antigen. So antigen is anything that's not self, and antigen is anything that will trigger an adaptive immune response. Okay, so these will be our microbes, or invading microbes. So we'll say binds microbial antigen. And in response, you guys, the B cell will start making a specific class of antibodies. I know right now this is really hard because we're talking about things we haven't gone over. But we'll describe you guys, there's 5 classes of antibodies in human, right? The first antibody a B lymphocyte makes is called IgM. Now, IgM, you guys, I do not mean to be disrespectful. IgM, it's a beautiful antibody. It's made, it looks like a snowflake. It's made up of 5 subunits, but it's huge. It's a huge antibody, the biggest one of all. And as a consequence, you guys, it's found mostly in the blood, within the blood vessels. You don't get a lot of it diffusing into the extravascular tissues, right? Which is where you're going to have a lot of microbial invasion. And furthermore, you guys, we're going to see it cannot carry out all the wonderful functions of antibodies, right? And the third kind of disadvantage of it, you guys, is moms can't pass IgM across the placenta to their babies. There's no transplacental transfer. And you guys, transplacental transfer is essential if our babies, when newborn, are going to survive. But this is transplacental transfer. So we're talking about all the babies developing in utero. The baby has to have mom circulating the antibodies on it when the baby is born. Immediately? Okay. So you're right, and you're talking about Thursday's lecture. Okay? Yeah. Okay. So you guys, this is an okay antibody. It's not the best. What we really want is for the B lymphocyte to undergo a process called class switching. We want the B lymphocyte to switch from making IgM to making the best antibody called IgG. Okay? So class switching. We want our B lymphocytes to switch from making IgM to making the best antibody, you guys, called IgG. Guess what this switch requires? What's the theme here?
Helper T cell.
Yeah, T helper cytokines. So the B lymphocytes, you guys, they cannot undergo this class switching unless they have guidance by the T helper cytokines. Now, why is IgG the best, you guys? So we'll say it's the best because it has the greatest variety of functions. It is the only antibody that mom can transfer across the placenta. It's the only antibody. Only antibody passed transplacentally from mom to baby developing in utero. Right? right? So this is really our key. You want an antibody that can carry out all the different functions, which we eventually will talk about. IgG, you guys, is the only antibody mom can pass across her placenta to the baby.
Is that what's passing through vaginally when she's giving birth?
No, across the placenta. What you're thinking about right now is secretory IgA.
Okay.
No, it's okay, because that's a whole other cool maternal antibody. But right now, we're talking about baby developing in utero.
Just
Yeah,
inside.
yeah, exactly. Okay.
Sorry, yeah.
So you get, no, that's fine. And furthermore, you guys, remember, like, one of the key advantages of adaptive immunity is immunological memory. What do we need, you guys, for immunological memory? Memory cells, right? So what do you want to make? Memory B cells. Guess what you have to make memory B cells? That's it, you guys. Yeah, so on the final exam, you guys, anything immunological and you don't know the answer, say T helper cytokines, and 9 times out of 10 you'll be right, okay? So we also want to make B memory cells, right, for that really strong secondary response. And what does that require? Yeah, you're not going to get any memory cells made unless you have guidance from the T helper cytokines. Does that make sense, folks? Okay. All right. And then, now you and I feel bad I'm going to do this to you, but I'm going to do it to you. So you guys, cell-mediated immunity. We're going to do it pretty superficially, but what I want you to know, you guys, the way we do it superficially is about all you'll really need to know for cell-mediated immunity on the final exam. So, like today, if you haven't had it in AP yet, you're like, oh my gosh, is she kidding? But Thursday, we will have a chance to actually look at the PowerPoints that discuss CMI. So today it might be kind of overwhelming, but just hang in there, you guys. It'll be all right. So you guys, so now we're going to leave humoral immunity, and now we're going to go to cell-mediated immunity, right? Okay. So let's first take a look, you guys, at our cytotoxic T lymphocytes. And we first want to ask ourselves, well, what are they doing? How are they helping us, right? So an important job they have is to recognize, say this is a human cell. So here's the nucleus. One of their jobs is to patrol and try to identify our cells that have been invaded by intracellular pathogens. And I'm going to use a virus, you guys, right? Perfect intracellular parasite. All right. So the strategy is, and again, you guys, kind of sacrificial lamb here. This infected human cell wants to alert the immune system. I'm infected, you need to kill me. It's like the Alien movie. Remember you guys in the Alien movie, that guy was infected, like, kill me, right? And they didn't get him in time, right? So the alien got out and spread everywhere. Well, that's kind of what this infected human cell is doing. It's trying to alert the immune system, I'm infected, you need to kill me. Now, why would that make sense, you guys? Why does it make sense to kill your cell that's infected with a virus? That's right. The virus has to have your cell to replicate, right? So if we can kill your virus-infected cells early enough, we can stop the invasion, right? So that's the key here. Now, how will your cell let your immune system know I'm infected? Brilliant. Yeah. So what your cells can do, you guys, is present some of the viral antigens, proteins, on, remember food? I love food. On a serving platter. So you guys, your cells can make this special little serving platter. You do not have to worry about the name. You do not have to worry about the name, you guys, but I'll use it. It's called an MHC class 1 molecule. It's the serving platter. And its function is to present the viral antigen on the surface of the cell. That's the tag. That's the tag that tells your immune system, and I'll just put like a whole virus, you guys. It wouldn't be the whole virus, it'd be just viral proteins. But that's the tag alerting the immune system, I'm infected, you need to destroy me, right? Okay. Now, the role of the cytotoxic T lymphocyte, you guys, and I'm sorry I made this so big, I'm gonna have to make it a little bit smaller here, is the cytotoxic T lymphocytes, they have these specific surface receptors, and they're called T cell receptors, or TCRs. And just like the old lock and key, a T cell will have a receptor that can only bind to a complementary antigen, right? Like the old lock and key, right? So we're going to be hopeful that circulating, you have a cytotoxic T cell that has a T cell receptor that can bind to that viral antigen being presented, right? So then, and we're simplifying this, you guys. We're skipping some steps. But the job of the cytotoxic T lymphocyte then is to release toxic molecules that will destroy that infected cell, right? But guess what guidance they need? What kind of guidance do they need, you guys? To carry that out? Right, they're gonna need the T helper cytokines, right? And so when they bind the antigen, they get the chemical message from the T helper cytokines. We'll just talk about two of the toxic molecules they release, you guys. The first toxic molecule they release is called perforin. And what perforin does, just like the membrane attack complex, it forms pores in the cytoplasmic membrane. Okay, so the cytotoxic T lymphocyte, the T cell releases. So these little red dots, you guys, are called perforin. What does perforin sound like? Perforate, you guys, so it's a perforated paper, like you're gonna make a hole in it, right? So the perforin, just like the membrane attack complex, it forms these little perforin pores in the cytoplasmic membrane. Could that cause lysis? Yeah, it could, right off the bat, right? But do you guys remember how we said very often the immune system, it has a backup plan? And we use the analogy of a 1-2 punch, right? If the first punch doesn't kill the pathogen, you have a second punch, right? That's the same with our cytotoxic T lymphocytes, you guys. The second punch is, let's see here, I'm running out of colors here. So the second punch is a substance called granzyme. Okay, and we'll use little black dots, you guys. So the granzyme that the cytotoxic T lymphocyte releases, now it can enter into the infected cell through those perforin pores, right? And the granzymes, you guys, what they do is they trigger cell suicide or program cell death or apoptosis. So it's the trigger for the cell to say, I'm going to kill myself. I'm going to destroy myself, right? So the granzyme then, you guys, that's the second punch. If the perforin doesn't destroy the cell, the granzyme makes sure that the cell will kill itself, right? And again, it's a little sacrificial lamb. Why is that helpful, you guys? That's right, because if this host cell is dead, can that virus replicate? No. And again, you guys, if you can activate this early in infection, maybe just a few cells will be infected, but then the virus can no longer replicate. You might not even know you were infected even, right? Does that make sense? Yeah. But you guys, is this also part of the double-edged sword of the immune system, right? Like in viral infections especially, a lot of the damage to our cells is a product, some of it's a product of our own immune response, trying to kill those cells before the viruses can replicate. Yeah.
Can that go into an endotoxin type scenario? Or no?
Let's see here. This would not be an endotoxin type scenario. Yeah, yeah. I mean, that's really good. You guys aren't integrating, but this would not be an endotoxin scenario. Yeah. Okay. So you guys, I know. We just have one more to do. Okay. So you guys, that's our killer cytotoxic T lymphocytes being activated by the T helpers. The last scenario, you guys, of how T helpers help cell-mediated immunity is in activation of resting macrophages. Now, it turns out, you guys, that most of the cells of our immune system, they're in kind of this resting, unactivated stage, right? You don't want cells of your immune system being overly reactive. That's how we end up like with autoimmune diseases and inappropriate immune responses. So you don't want them turned on until the right time. The problem is, you guys, sometimes some pathogens can replicate inside these resting macrophages. And again, you guys, a classic example is Mycobacterium tuberculosis. So let's say this is a resting macrophage in our lungs, an alveolar macrophage that hasn't been activated. And the problem is they can still carry out phagocytosis, kind of slow, low phagocytosis, but enough so a resting macrophage could ingest some Mycobacterium tuberculosis. And it's kind of like the macrophage, it's kind of asleep. When I get up in the morning, I'm truly not awake yet, but I can get my slippers on, I can change into my street clothes, but I'm really not awake yet. And that's kind of like the resting macrophage. It can slowly phagocytize, and it's really not awake yet. It's not really, really functional. So what I need in the morning, you guys, is high caffeine coffee to wake me up, right? I have my cup of coffee on, wow, okay, now I got to get ready for school, need to brush my teeth, et cetera, right? So you guys, the T helper cytokine provides that high caffeine coffee to the macrophage. And the high caffeine coffee, you guys, it's interferon gamma. So gamma interferon, that's the high caffeine coffee that the T helper, excuse me, will deliver to the macrophage to activate it, to wake it up, okay? So this activates the macrophage. And what do we mean by activate? Yeah. So when an activated macrophage, you guys, they're going to increase production of those hydrolytic enzymes, those lysosomal enzymes. They're going to increase production of those toxic reactive oxygen intermediates like superoxide anion, hydrogen peroxide, even bleach-like substances. They physically move faster, you guys. They become more efficient at phagocytizing surrounding microbes. And some authors describe these activated macrophages as angry killers. Angry killers, right? They're efficient pathogen killers now that they're activated. But who had to activate them, please? The T helper cytokines, right? So the take-home message here, you guys, is who in this grand picture, who does HIV, or let me see, who's the key cell, you guys, in all of these adaptive immune responses? The T helpers, right? And who can kill the T helpers? HIV, right? So if we've been chronically infected, you guys, with HIV, right? Normal T helper count, you guys. So normal CD4 positive T helpers should be about like around maybe 1,200 T helpers per microliter of blood. That's a healthy, strong immune system. In chronic infections, HIV keeps destroying our T helpers, destroys them. So we experience immune collapse. We have acquired immunodeficiency syndrome when our T helpers drop below 200 T helpers per microliter of blood. Now, our orchestra, our symphony, all the cells in the immune systems, they've lost their leader. And consequently, they cannot respond appropriately, even to low virulent, opportunistic pathogens, right? So just think, you guys, no class switching, no memory cells in humoral immunity. Over here, and you guys, I forgot, one more thing, the cytotoxic, one more thing the helpers do is they help trigger memory cells to make T cytotoxic memory cells. We need memory cells of them, right? So not enough T helpers, we don't get T cytotoxic cells killing our cells early, right, that have been infected with pathogens. We don't get activation of our macrophages, right? So people that are infected that have AIDS and tuberculosis, they often die rapidly. Yeah. So again, you guys, so we say the T helper is the Achilles heel of the immune system, right? By wiping it out, you really wipe out all the adaptive immune responses. Kristen, yeah.
So the CD4 positive and the CD4 positive T helper cells, that refers to the human surface receptor protein CD4.
Yeah, and the CD4, you guys, if we have time, the CD4 is an HIV receptor. In normal immune functions, it's playing a different role, obviously. So on Thursday, I can show you a slide of how the CD4 is involved in interactions of T helper lymphocytes with other cells of the immune system. The CD4 actually helps them interact with their target cells. Okay? All right. Okay, guys, so what we'll do then on Thursday, guys, is we'll talk about the antibody structure, antibody function. We'll talk about how the B lymphocytes get triggered to make their antibody. We'll talk more about primary, secondary immune responses. And then you guys will just briefly go over CMI again, about at this level, but we'll actually have some slides that you can look at instead of trying to copy down my chicken scratches up here. Okay. All right, okay, so